Hi, this is Ashley Gibbon. I'm the Development Manager, and in this training we're talking about the principles of precision. This is the second in a series of trainings that we're doing on how we develop, validate, and maintain our laboratory tests. So here's our topics. We're going to talk about the difference between precision and accuracy, how we measure precision, the different types of precision studies that we do in validation, how we use precision information in our troubleshooting, and then how we monitor precision once an assay is live using our controls. There are two CLSI documents that reference precision. One of them is the evaluation of precision of quantitative measurement procedures. And the second is user verification of performance for precision and trueness. So CLSI is the Clinical Laboratory Standards Institute, and they have many, many papers on how to do just about anything in the laboratory. And they're recognized by all different regulatory bodies. So basically, if you're following their guidelines, you're going to be able to pass your inspections. So let's start with what's the difference between precision and accuracy, because these are two terms that I hear confused every now and then. But in the laboratory, they're very different things. So it's important to understand the difference. So precision is a measure of reproducibility. So if I have a test and I take one sample and I run it 10 times, do I get pretty much the same value every time? Accuracy is a measure of correctness. So if I take that sample and I run it as an unknown, do I get what I was supposed to get? So a lot of times when we're talking about accuracy, we're running things like reference standards or proficiency testing. So the difference is accuracy, am I getting what I'm supposed to get? And precision is, do I get the same thing every time? And obviously in the laboratory, we want to have both, but understanding the difference between those two measures will help you when you're trying to troubleshoot a problem in the lab. So a classic example of this is the dartboard. Say we're out and we're throwing darts, and we get this sort of pattern. So accuracy is a measure of how close are my points to the bullseye. So in this case, not very close. So this is pretty low accuracy. Precision is looking at how spread apart these individual points are. So in this case, you can see those points are all over the dartboard. So this is low precision as well. This one, on the other hand, we're still not close to the bullseye, so it's still low accuracy, but you can see how the points are all clustered up together. So this is higher precision. So I'm getting the same thing, it's just not correct. This, on the other hand, we got close to the bullseye, but each individual point is different from the others. So this is high accuracy, but low precision. And this is obviously what we want in the lab, is high accuracy and high precision. But it's important to understand the difference between accuracy and precision because they mean very different things when you have a problem in one area but not the other. So in the cases where you have low accuracy and low precision, like the top left dartboard, if you see this sort of pattern when you're validating a new test, obviously we want to see if there's a way to change the method, improve the procedure to get higher accuracy and higher precision. But if you try multiple things and you really just can't get it to work, this sort of pattern is often indicative of a qualitative test or sometimes a semi-quantitative test. So that might be something to consider if during validation you just can't get those points tighter towards the target. The dartboard on the top right, the low accuracy, high precision, this typically when we're troubleshooting is indicative of something systematic. So all of those points are moving together. So that might be something like a calculation error that's getting applied to all points. The most common time we see this sort of pattern is when we've brought on a new lot of calibrators and our target value, let's say, is 25, but in actuality it's about 28. And so all the points are going to move together to the same area. The dartboard in the bottom left, the high accuracy, low precision, this, on the other hand, the points are not moving together. We're still close to what we should be, but they're different every time we run them. And so this is a little more random in what's going on. When we see this sort of problem in the lab, this points to something in the procedure, either the processing or the instrument. So some examples of times we may see this is on a chromatography assay, for example. You may have a syringe that's got a little bit of gunk in it, and so the plunger is not going down the same amount every time. Or a 96 well plate where your plate washer has one little nozzle that's clogged up, and so that particular well, say well D4, just isn't getting cleaned as well as the other wells. So it's something that's kind of random but can introduce imprecision into your assay. So understanding the difference between, do I have an accuracy problem, or do I have a precision problem, or do I have both, helps you take your first steps towards fixing the problem. So how do we measure precision? We use coefficient of variation, or CV. You might see this in the literature too as RSD, or relative standard deviation. It's the same calculation, but the CLSI guidelines and CMS both refer to CV, so that's what we refer to. And at Genova, we typically represent this as a percentage. It takes that standard deviation and puts it in context of your average. So it sort of makes your standard deviation show you what the true representation of your spread of samples is. So where do we have imprecision in the lab? It can come from a lot of places. You can have imprecision that comes from your sample. If you don't have it well mixed, well homogenized, then every time you go into that sample with your pipette, you're going to get a different level of analyte. So it's important to mix and stir your samples as much as possible. You can get imprecision from the sample prep. It's just talking about extractions or solid phase extractions or binding curves. The more complex your sample prep, the more opportunities to introduce imprecision into the procedure. You can have imprecision from your instrument. So again, things like your syringe or your lamp or your automated reader. And you can get imprecision just from the human element. Now, I'm not referring to human error. We'll talk about human error in my next talk on accuracy. Here I'm talking about just the variation between tech to tech, or even within the same tech. As you guys know, some people are just more consistent than other people. You may be having a bad day today or a really great day tomorrow. And just tech to tech, there are differences. We've discussed in the lab differences in, for example, pipetting technique. And you can go into a lab and watch them pipette. And while they're technically following the SOP to pipette 100 microliters into that tube, you can watch the techs, and sometimes they're blowing it out, sometimes they're rinsing it. There's just different nuances to the way they're holding their pipette or dispensing the solutions that can introduce some imprecision. So in places where this is critical, we want to spell that out in the SOP, exactly what that technique should be. But it's very difficult to address all possible human iterations of laboratory work. So just understand that there's some imprecision that comes from human. And of course, you can have imprecision due to monkeys in your lab. So when we're validating a brand new test, we want to understand not only the total imprecision of this assay, but how much imprecision is introduced by each of these individual components. So when we're running validation experiments, we're going to run experiments that isolate just these individual pieces so that we can then understand their contribution to the total. So there are three basic precision studies that we do during validation. One to look at the sample prep, one to look at the instrument, and one to look at the total precision. First of all, we're going to look at the sample prep. We call this intra-assay because it's within one run. So we want to look just at the imprecision that's coming from the sample. This includes the sample mixing and the sample prep, so your extractions and preps. So in order to do this, we want to hold everything else constant. So we're going to run We're going to take 2 matrix samples at different concentrations, and we're going to prep these samples 20 times and run them all in the same batch. And by running them all in the same batch, this means that it's one technician, it's one set of reagents, it's one calibration curve, it's one set of controls, it's one instrument. We're holding everything else constant except just prep to prep to prep. So we may be talking about multiple tubes, multiple vials, but you want to replicate that same prep of the same samples. And we're going to look at the CVs. So that may look something like this. In this case, I ran 2 matrix samples, the C1 and the C2, and an aqueous sample. And I find it helpful throughout validation to always include both a matrix and an aqueous solution. It's not necessarily required as part of the regulations, but I find it is very helpful to help illustrate if you're going to find any sort of matrix differences between the aqueous and a urine, or an aqueous and a blood. And typically that's what you see during precision. As you see here, the aqueous had a CV of 7%, and the 2 matrix samples were 10 and 12%. We're also going to look at the instrument precision. So we're going to hold all other things constant. So we're going to hold the sample prep constant. We're going to prep 1 prep of each sample. So 2 samples, 1 prep each. And then we're going to make our instrument analyze each one of those 20 times. So what I mean by that, if you're talking about a chromatography assay, that's 1 vial, and have that instrument inject it 20 times. If you're talking about an EIA plate, we're going to have the plate reader read 1 well 20 times in a row. If you're talking about an automated platform like your Olympus or your Architect, we're going to program it to read the same tube 20 times in a row. So this is holding everything else constant and just looking at the instrument to eliminate imprecision from everything else. We typically see much lower CVs on the instruments. This is why we spend so much money on highly accurate, highly precise instruments. Typically, we expect CVs to be less than 5%, as you see here. Next, we look at inter-assay precision. This is total precision. This is going to demonstrate the cumulative effect of everything that you're doing that can contribute to imprecision. And what this does is give us a good idea of what we can expect when this assay goes live. What kind of CVs do we expect from proficiency testings, from competency assessments, any sort of splits, anything like that. So in order to get the best possible representation of what the imprecision in production is going to look like, we want to introduce as much imprecision to this experiment as possible. So we're still going to take 2 matrix samples and an aqueous, that's what I like to do, and we're going to run them 20 times across multiple batches. So a batch we're defining as having separate calibrations and separate QCs. And so you may take 1 of each of your samples and run it on a batch, and then shut your instrument off, turn it back on, recalibrate, re-QC, and run that batch again. Ideally, as I said, we want to introduce as much normal variation as possible. So the best way to do inter-assay is to run it on multiple days, multiple calibrations, multiple QCs, multiple techs, multiple instruments, multiple kit lots, anything that you expect to just be normal variation once this assay goes live. Let's introduce it at this point, because that will give us a much more realistic view of the performance of this assay. And that might look something like this. So again, our aqueous and 2 matrix controls gave us CVs of 11 to 17%. And so those are the 3 experiments that we run with every validation. This is sort of our minimum. And what it ends up giving us is what the CLSI guidelines call precision profiles, which looks something like this. And so this really lays out what is the imprecision that we expect from the sample prep, what is the imprecision we expect from the instrument, and what is the total imprecision of the assay. And this is really helpful information when things kind of start going wrong, and you can help figure out, tease apart, where do you think your issue is. So beyond these 3, depending on the assay, we'll often do additional studies. And really, when you're thinking about your assay, let's think about where are other contributors to imprecision. So we may look at different instruments. If there's going to be multiple instruments running the same test, we'll run the same batch of samples on all instruments. You want to look at different texts. This is going to be addressed at your competencies to say the same set of patients is going to be run by multiple people. We're going to look at different lots. If you're looking at an EIA kit or an RIA kit, something like that, make sure that your validation includes multiple lots of that kit. If there's a critical reagent, say like an antibody, you might want to make sure that you've got different lots going on. And during chromatography assays, always make sure that you're including different lots of the columns. Beyond that, you may even want to break it down even further into individual steps of the procedure. So the example I have here is on our commensal assay, where we take stool and we extract the DNA, and then we run it through the PCR procedure. And so maybe we understand the total imprecision coming from the sample prep piece, but we want to break it down further to say, within that, how much imprecision is coming from the extraction and how much is coming from the PCR. And so in that case, what we might do is take 2 samples, take them through the DNA extraction process, and then PCR them 20 times, just to understand just that one piece. Where is our imprecision? Okay, now that we understand precision and we understand how we assess it and we set it during validation, how do we use this information when we're troubleshooting? Well, I've got a case study here. So we had a test that began to sporadically fail. There wasn't any obvious reason about when it was working and when it wasn't working. We looked at all the reagents and realized we hadn't changed anything critical recently. But the last flag came when the backup technician was having trouble passing her routine competency, which had never been an issue before. So we got a set of samples, and we had that same set run by the lead technician, the backup technician, the development technician that was helping out with this project, and the supervisor. And it was bad, y'all. The CVs were all over the place. So you can see here the CVs range from 1% to about 53%. It's just all over the map. And we tried to see, do any of these two match each other? And they didn't. And so if you remember the dartboards, when we were talking about the difference between precision and accuracy, this just smelled like a precision problem. You know, if those CVs had all been 22 to 26%, you know, still bad, but at least consistent, we might have questioned more of an accuracy issue. Like maybe something is pushing everything off by 22%. But in this case, it's all over the place. It's that first dartboard, you know, where I'm just throwing darts everywhere. So we said, okay, we think we have a precision problem. So the development tech ran those 2 precision studies that we just talked about. He took 2 samples at 2 different levels, and he prepped them 20 times on the same batch. And we got CVs of 23 and 24%. And for this assay, that's pretty bad. Typically, this assay had CVs around 15%. So then we said, okay, take 1 vial of sample 1 and 1 vial of sample 2 and inject them 20 times. This was on an HPLC. So let's take 1 vial of sample 1, inject it 20 times, and then 1 vial of sample 2 and inject it 20 times. And it also had pretty bad CVs, 17 and 19%, and you might be able to argue that's a little better. But remember that with instrument precision, we expect CVs to be more in the range of 5% or less. So this is pretty bad. But this is enough information to know how to move forward. So I'll give you a minute and let you decide whether you think, do we have a sample prep issue, an instrument issue, or both? So the important thing to remember here is that on the sample prep precision, those are 20 different preps of the same sample, but they're also 20 separate injections. On the instrument precision, this is 1 prep with 20 injections. So that means in this case, the instrument precision study sort of trumps the sample prep precision, because if you see CV issues on your injections, you're going to see them on your preps as well. Okay, so we said, all right, we've got an instrument problem, and we called up our instrument technician. We cleaned the instrument, we replaced the column and flushed out all the lines. We gave it a good preventative maintenance. It's passing all of its instrument checks. And so we repeated that instrument injection study where we took 2 vials, inject them 20 times right after each other. And it didn't fix the problem. At this point, we're sort of like, what in the world is going on? Like, we really thought that was going to work. But this is troubleshooting sometimes. So then we sort of regrouped and we got together and we said, okay, what in the world do we think is going on here? Is this something in the instrument that we didn't address with the preventative maintenance? Is this something inherent to this particular method? So we decided to continue to follow the instrument path, and we loaded this method onto another instrument. And this is another instrument that doesn't typically run this assay, but it's the same make and model, so we figured it would probably work. So we loaded the method up, and we repeated that injection study where we took 2 vials and injected them 20 times. And voila, it's much better. So now we have actual proof that there's something different about instrument 1. Because you see instrument 2, CVs of 3 and 4%, which falls right into that less than 5% that we were expecting. So this is proof. Something's going on with instrument 1. So we placed a service call with the manufacturer. They came out and they replaced some key components in the detector, some of the optics, that sort of thing. And then we repeated both precision studies. And this time we got the results that we expected. CVs on the sample prep below 15 and CVs on the instrument precision below 5. And so this is a good illustration of how you can use precision data to sort of drive the direction of troubleshooting and decide which path do I want to go down, the sample prep path, the instrument prep, or do I have a problem with both? Usually when you're troubleshooting, the most difficult decision is that first one, is when you get that first terrible set of data to even identify, is this precision, is this accuracy, is this both? So once an assay is in production, how do we monitor in precision? Well, we use the controls, and I think we often think of controls as more of an accuracy check. I've got my control and I'm running it, and it's got a target value of 10, and I have an acceptable range of 8 to 12. So as long as I'm within that range, we're good to go on my run passes. And we certainly look at it that way. But the controls are also monitored weekly by the supervisors and periodically by the lab directors, and they're looking not only at the accuracy, but also at the precision. So they do this in 2 ways. When we're establishing a new lot of controls, we often run them as unknowns, say 20 times, to set the new target ranges. And again, we're not only looking at the target concentration for accuracy, but we're looking at the observed CVs to make sure that that control is performing where we expect. So here's an example. We ran this new control 20 times, an average of 22.9, and a CV of 12%. So is that good? Well, I don't know, right? So my point here is that CVs, like standard deviations, are very helpful measures, but not in a vacuum. You really have to look at your CVs in context of your assay. So for some assays, CVs of 12% are really awesome. Sometimes that's completely unacceptable. So let's look at this CV in context of our greater assay. One way I might do that is look at how is the current control running. So the current control, when we ran it 20 times to establish the ranges, had a CV of 11%. And then once we put it in production, it's been running for 6 months or so, it's got a CV of about 15%. So this CV of 12% that we got on the new control is falling right in line with that. We might also look at previous controls. So here are 2 previous lots of that same control. Again, the CV when we're establishing somewhere 11 to 15%, and then once you're running it goes up to about 15 to 19%. We can also take a look at how that particular control was running during validation. You can see this falls right in line. So in this situation, I'd say, yeah, that CV of 12% looks right on line. The reason this is important, though, is that let's say that our CV is too high relative to past performance. So here we have a CV of 23% on the same control. Now, 23% may or may not be within the acceptable range, but it's certainly not within the range that we're expecting. We usually expect this, as we said, somewhere between 11 to 15%. So in this case, we want to take a look, are there any of these points that maybe are spurious that we should throw out? Did something change in the assay? Can we explain why there might be a higher CV? Maybe we want to run additional points to see if collecting more data will bring the CVs back to what we expect. On the flip side, you can't have CVs that are too low based on past performance. So, I think in the lab we tend to say, hey, I got a great CV here, thumbs up, we're ready to go. But, in reality, what we've seen in the previous 4 lots is that CVs of 11 to 15% are more typical. And so if we saw a CV of 7%, as in this example, if you set your ranges at 7%, you're going to start failing your batches because that's not what we're used to seeing in our assay. Now, if you've made improvements to your assay to improve the precision, then that's great. Let's launch with CV of 7%. But if you can't explain why it's running tighter than usual, then you probably want to raise this to your supervisor to say, what's going on here? Do we need to run more points? That sort of thing. The most typical time that I see something like this is honestly when we're about to run out of the current control, and so we're just trying to get this new control on really quickly, and so maybe the same person ran all 20 observations, or it was all run on the same instrument. We didn't, as I was talking about during validation, we didn't introduce enough regular imprecision into the assay to give us a true representation of what the CV is going to be. So in this sort of case, if that's what happened, then maybe we want to run some additional points with a different technician or on a different instrument or on a different lot of kit, just to introduce that expected imprecision. And then once the controls are live, the supervisors are monitoring them weekly. So this is a screenshot from TQC, which is the QC module from SCC. And the green range is our acceptable range for this control. The yellow bars are our 2SD range, and the red bars are our 3SD range. And each of those little dots is a different control from a different batch. And so the supervisors, when they're reviewing their control every week, they're looking not only are they pretty much falling on the mean, but how is the spread? So that's how is our precision looking? And so in this case, it's pretty well spread from across the green bar. I'll show you some examples of some that probably aren't as good. In this example, you can see that our acceptable range is between the 2 yellow bars, but all of our points are falling between the mean and the bottom SD. So this is telling us that, number one, our mean is set too high, but also that our CV is set too wide. The spread is not quite what we set it. So TQC actually gives us this information. So you can see here our assigned mean is 2.71 with a CV of 15%. But in the last 2 months, the mean is actually running at 2.28 with a CV of 9.3%. So in this case, it looks like it's been pretty steady for the last 2 months. So I'd probably adjust the mean down and then adjust the CV to say 10% to be more representative of how this assay runs. The trouble with leaving CVs this wide is what happens if you get a point that all of a sudden is up at the top 2SD range. It's still in, it still passes according to this criteria, but it's markedly different than the way that the assay is normally running. So by appropriately setting your CVs, you're sure to control for when things just don't look right. You can also have the other issue where your CVs are too narrow, and so your spread is actually wider than you expect, as you see here. So here, we have an assigned CV of 11.5%, but it's actually running at about 15.1%. And it looks like we've only had this lot open for about a month. So maybe we didn't appropriately set the CV when we first ran it as unknowns. So in this case, I'd probably take a look at this particular control for this particular analyte and say, historically, what are the CVs? And if the CVs are typically closer to the 15%, I'd probably go ahead and widen it out. If, however, the CVs are typically more in the 10 to 11%, then you need to take a look at your assay and try to figure out what has introduced some additional variation. CVs, again, can't just be used just on their own. You have to be looking at them as part of the larger picture. So in this case, for example, this control, if I were to just look at the mean and the CV of this running control, it would look like everything is perfectly fine. Mean is right on, the CV is right on, but clearly there's something going on with this control, right? So supervisors, when they're watching their controls, not just looking at the numbers, they're also looking at how are they behaving? Are they trending? Are they dropping? Have they shifted? In this case, clearly they have dropped. Here's another example of this. So there are three different instruments. There's a green, there's a yellow, and there's a red. And again, if I was just looking at means and CVs, I would say, hey, this control is running just fine. But what we noticed was that the points in orange, which represents GCMS number 12, were all running markedly different than the green and the yellow points. Still passing, still no problem, but it was enough that we noticed the pattern. So sometime around middle of January, it looks like, we did a preventative maintenance on GCMS 12. And then you see those red points jumped right back up in line with the others. We probably need to tighten this CV. But this illustrates that by watching the spread of your control and understanding what is normal for your control, you can catch problems before they become problems. Because in this situation, had we not caught that and done the preventative maintenance, that GCMS 12 points probably would have continued to drop till it was suddenly failing runs. You can also get situations like this, where the CVs are running just fine, and then something shifts. In this situation, we had a calibrator change, and it changed the values of our patients. And this is most evident quickly in the controls. So in this case, we need to go back and take a look at that change and make sure that it was appropriate. So my point in all this is to say that accuracy and precision, it's important to understand the difference between the two and why you might be looking at one versus the other. Although we want both, precision is really telling us how reproducible it is. But that being said, when we're monitoring precision, it's important to not just look at the CV number, but to understand it in the context of my particular assay and my particular patient population. So you're going to get training credit in UltiPro. The name of this training is Development Training Precision. Thank you.